Sanchar, and he's going to tell us about optical probe of quantum magnetic systems.
Is on? Yeah. Good morning, everyone. And I am Sanchar. I am currently a postdoc in the group of Christina Sarodaki. I should have a laser. Yeah. So temporarily, I'll be joining Madrid in a few months as a group leader soon. And the work I'll be presenting today was done. Well, most of what I'll present will be something that I've been doing in the last year with Christina. But also, I'll flash out some of the initial works which I was doing when I was a postdoc in Sylvia's group. And a big contributor of these works in the beginning was Victor Bittencourt, who's currently in Strasbourg. And this logo is poorly printed here, but it's a nicer logo than it looks. Yeah. Oh, these images are not really well established, unfortunately, but okay. So the kind of thing that I've been trying to think about in the last few years was to just have to be able to show some quantum effects in magnetic systems, to be able to develop protocols on how to do those things. For instance, a typical system would be if you start with a magnetization, you figure out some way to generate some kind of a quantum state, which could just be a superposition of magnetization, for instance, and also figure out how to measure it. Where I am showing here on the right side something called a Wigner function. For people who don't know what a Wigner function is, it's kind of a representation of a state. So superposition state is this kind of Wigner function, which there's supposed to be a plot here which is not shown properly. So you're supposed to look at this as this is the x direction of magnetization, and this is the y direction of magnetization. So you're supposed to look at it like a probability distribution, where you see these two peaks, which tells you that there's a probability of the magnetization being in these two spots. And you see these weird fringes, which tells you that it's a superposition of the two states, as opposed to a classical distribution where it's a probabilistic way. So this is like this is a very nice pictographical way to represent a complex-looking density matrix, which can appear sometimes. So let me just flash out some of the things which I did for state generation. Actually, only one thing. So you see here a setup consisting of microwave cavity, which I'm presenting as the mirrors, with and a superconducting transmon with a magnet. So this is a setup which was used by Nakamura group, and they've done amazing things with this setup. They've shown a lot of cool measurements. What our theory was about, a question was, can we use this transmon to create some arbitrary quantum state in magnet? So the question is, let's say you ask me, how do I create a superposition of magnetization, which is some quantum state? Then the algorithm will figure out what pulse input we should give to transmon, such that at the end of the whole evolution, you will end up with a magnetization state which you desired. This is the basic point, and of course, if you want to discuss more details, I'll be happy to discuss in the discussion time about this. Yeah. But now, one of the reasons why I'm flashing this also is to kind of point out something which Sylvia already pointed out yesterday, that in the same setup as the before, with the Nakamura group setup with transmon and a magnet, there was a group in China who showed a non-classical state of magnons. So what you see here in the bottom is what you expect. So if you have a zero state, then a Wigner function is supposed to be just a Gaussian function. It just gives you a probability at the center. If you have Fock state, on the other hand, you still have this kinds of a Gaussian but with a node in the radial direction. And the most important point is that it's negative at the bottom, in between. For those of you who don't know, the negativity of Wigner function is like a guaranteed proof that this state is non-classical. Classical system will never have negative Wigner function. And indeed, what they measured is something quite resembling what was expected, and they still see a negative Wigner function, which means that they have created a non-classical state, the magnons. So this is, as far as I know, the state of the art of the magnetic state generation. Yes, please. Okay, I'll try.
Looked at the reference yet, but did they look at the time dependence of this state, the 0 + 1?
No, they did not.
Okay.
This was, they just performed a tomography.
Okay, thank you.
Yeah.
Do you know how long it lasts?
Sorry. Okay.
Did you mention that in the paper? I don't remember this actually. I see. Is it gonna go forward? Ah, okay. So now in the previous two slides, I was talking about all the amazing, partly amazing measurement which has been done using superconducting transmon. And if you remember, the point of my talk is to use optical methods to perform any measurements on magnets. The point is, why do we care? If transmon is so awesome, then do we care about optical systems methods at all? So it's a okay, so this is more of like a horizon viewpoint of what would be eventual limits of what one can do with a transmon. So obviously a transmon is extremely sensitive to magnetic field, and that is why in their case it was electric field, but one of the other ways it's very sensitive to magnetization. But a transmon is still built out of a microwave circuit, so it's never going to be, it's not going to be as scalable as, for instance, an optical system, which you can go down to even sub-diffraction limits and much lesser. And there's another point of a transmon is because you're always coupling a system, so typically it will lead to additional dissipation on the system. You cannot control the dissipation that easily. You'll have to, okay, you can tune the frequency of the transmon and do it, but normally there's always additional dissipation by at least the microwave cavity surrounding it. So with the BLS, there's some of the advantages, at least just as a very vague starting point. So there's some advantages which are like there's kind of size independent until, let's say, the focusing limit of an optical light, because no matter how small you go, you can still measure system with the same efficiencies. And there's an important aspect which is interesting for quantum computing is there's a controllable coupling. So the coupling is switched on only when there's an input laser, otherwise there is no additional coupling. So there is no dissipation in, let's say, the off phase of the system. But obviously there's a big problem that it's not as sensitive. Optical coupling, at least in YIG, is not really that high, let's say, compared to magneto-optical materials which otherwise present. So what I want to do here is just try to see, like, even with a small sensitivity, is it possible to do something interesting, or is it just all waste? As a I'm a theoretician, I did not make it specified clearly, but yeah. For some of the people who don't know what Brillouin light scattering is, let me present a very cartoonish, simplistic picture of why does a spin interact with light at all. And a typical interaction mechanism is, what I'm presenting here is kind of like, imagine a hydrogen atom for the time being, which has some kind of an s orbital with some spin up system, and a photon comes in and it can excite a system from s orbital to p orbital, but does not change the spin, because the typical interaction of light with an atom is only through electric field, which does not affect spin at all. And in this scenario, there is no change in spin yet. However, if there's a spin orbit coupling in your system, that is when you can have these transitions where you can go from, let's say, a higher angular orbital state to a lower orbital angular momentum state and exchange the spin or something like that. And there will be some kind of a mixed state involving many spins and orbital. And this state, this now new orbital can, of course, also radiate out a photon and come back to the s orbital state in this case, but it can go to other states as well. It's not important. It's not important where it goes to, but the main point is there's a probability of the spin being flipped in this entire process. So, you know, if you squint your eyes and try to blur out all the internal parts, what's going on is that you have an incoming photon, then you have an outgoing photon, and the spin has flipped. And that's the entire process. To describe it mathematically, it will be like, you know, you are affecting the motion of photons because of the presence of spin. So it can be written as an effect of magnetization on the permittivity of the system, which for a cubic system with symmetry analysis, it turns out to have two free parameters, but okay, that's not so important. You can write it out. That's the main thing. So now I want to talk a little bit about what, let's say, is a theoretical limit of how much information conversion can happen. And I'm going to disregard literally all experimental issues which will appear here, which are a lot, I'm sure. But just to talk about, like, if you have just a light coming into the magnet, and yeah. So typically, if you have an coherent large laser input coming in, and there's a magnetization, it's interacting with the magnetization inside the magnet, and it's coming out. For the time, you can ignore this squeezed input coming in. They are just to reduce the vacuum noise. But if you ignore them, it's still completely fine. The output will look like it will have some component of noise, which is just a noise coming from impurities inside the magnet, optical noise coming from impurities, also part of the vacuum noise coming from outside, and a part of magnetization, which let's say is our signal, because that's what you want to measure. This theta is of course the signal to noise ratio. Yes, please.
Is that the creation operator? I mean, what is A out?
Yes, sorry. Yeah, it is a creation operator of the output field. Yes.
Okay,
so,
thank you.
And this noise is also a creation operator of a photonic field, but okay, it's noisy.
And then M operator is M signal. What is that exactly?
Yeah, it's the annihilation operator of the magnon in this case.
It's the creation or annihilation?
Annihilation.
Okay, thank you.
Yeah. So to give again like a theoretical limit of what this theta could be. So what will it depend on? There is this theta here, which is proportional to lots of terms. The first term here is just a coupling, which is a material constant. So theta here is the Faraday rotation or the Cotton-Mouton effect. It's something which just tells you how strongly optics, how strongly photons couple to individual spins. That's a material constant. The second term are the vacuum fluctuations of the magnetization. So it's basically like if to create a magnon, if it involves a huge fluctuation, then it's easier to couple to it. If it's a small fluctuation, it's going to be a smaller coupling. So that's why these vacuum fluctuations enter here. Just a Bohr magneton divided by the saturation magnetization, which is, I guess, almost like the inverse spin density kind of a thing, but a square root. The last term is what I've added to decide the optical power. So in this entire mechanism, if you input large power, then you have large output, because the number of scattered photons are just proportional to the number of photons which are coming in, because that gives you the, if there's a high number of photons coming in, then there's higher probability of scattering. So obviously then if I just keep increasing the power in my theory calculations, then it will just keep increasing the coupling, but that's quite bad, because then it will just lead to optical heating. So here I put a factor to say like, allow me to input as much power, which will lead to a temperature change of a small temperature change, let's say 100 millikelvin temperature change, which will not affect the magnon state so much. And to calculate that, okay, I can take the specific heat of the material, the density of the material divided by optical absorption, because optical absorption will tell you how much heat is being dissipated into the system. This is of course a purely, this is heat dissipated only inside the magnet. It's not taking care of any of the outside electronics which will appear, which obviously is going to limit the power as well. That's why it's a theoretical limit. For YIG, this turns out to be 0.2. So you have signal to noise ratio of around 20%. And this is, without a cavity. It's just in free space. So without a cavity enhancement, it's not terrible, at least, but it's of course probably very experimentally challenging to achieve. Yes.
Sorry for keep interrupting you. I'm just trying to understand. So, is this an extensive or extrinsic or intrinsic quantity? So, does it depend on the amount of the material?
No, it does not. Yeah. So if you have a higher material, then you have, let's say it's a nonlinear coupling, so it goes as 1 by square root volume. But with a higher volume, you can also input in more power, because it does not lead to heating in the system. So it's like the power would be something in watts per volume, right?
So it scales like a cavity coupling, but it's non-resonant, right?
Non-resonant. Yeah, optics is is far.
Yeah, it's
infrared,
right.
let's
There's
say.
no resonance with any magnetic
No.
or internal band transition of anything. It's just yeah.
Yeah. This formula will still hold even if you're close to the band gap. But okay, as long as it's not touching the band gap, because that is when you have excitations. Yeah.
Thank you.
But I'm generally assuming it to be in between the band gaps, so it's a bit more transparent. Yes. Ivan?
So people have done work on trying to do transduction with the, right, turning microphotons into optical photons via the magnons.
Okay, yeah.
How does this parameter compare to the metrics that are important to them? It's not a too waffly a question, right? I mean, they're obviously related somehow, right? Because here you're looking at turning magnons into optical signals, and they're looking at turning microwaves via magnons into optical signals, and the first part of that process is kind of easy, right? So
Yeah. The coupling, you mean talking about only the optical interface, right? The microwave to magnon interface is of course very strong.
Yep.
In that case, but it's mostly the optical interface is what you're talking about.
yeah.
Yeah. In their system, I think it was like 1,000 times smaller than this estimate. And from what I understand, the main reason, from what I at least understand from by talking to Koji Usami there, that they cannot input a lot of power because of the optical fibers and every electron is before which comes into the magnet.
Okay.
Yeah.
Yep. Cool. Thanks.
Okay, I'll go forward. Maybe I can increase this a little bit. Thing. No. Okay. So again, now there's a lot of theory about. So what I previously showed you was just there's an output coming in from input photon, and now there's a part of a theory which I'm not explaining in this talk, but I just want to flash out that we can use this equation and then use some data analysis on the output photons to try to figure out the density matrix of the magnon, which could have been. Yeah. So for instance, if the magnon was, I'm again describing Wigner function here. So if the magnon, like I just theoretically in my simulations, put that magnon is in a superposition, is in a CAD state, and then try to look at what the output photons are coming out. And then use the data to try to reconstruct the input magnon state. And I'll be happy to discuss how I do it or what the details are, but I just wanted to see like kind of the bit of a learning about quantum information that at least I got while working on this project is that even for a small theta, a very small signal to noise ratio, the algorithm is able to predict easily the peak positions of the magnetization. But in the prediction, you see there are no fringes. So that means the algorithm thinks that it's not a superposition, it thinks that it's just a classical probability distribution. Yes.
So you are still plotting the Wigner representation?
Yes.
Okay.
I'm just trying to wrap my head around what are the assumptions that you have, because you're saying theta is an intensive quantity, so it doesn't depend on the amount of the material. But this is kind of like a signal to noise measure, and I'm struggling with that because just in practical experience, I know that the amount of material matters because of the interaction length and all of that stuff.
Yeah.
I also want, so my intuition, and I'm not saying anything about what you're presenting, but my intuition that maybe is wrong that you can address is that that like Faraday or Cotton-Mouton effect is extremely weak interaction. And so I would expect that it's going to be not possible to do more than measure an expectation value. And I'm wanting to understand what you're plotting. Is it, so when people measure this with qubits as the ancilla to do the cavity measurement, what they're really doing is they're doing a series of single shot, and Hans can correct me because I actually haven't done this, but you know, he has. They're doing a series of single shot measurements to get like, and then they go over and over and build up a histogram essentially to build up the Wigner function. And I want to understand what it is that you're talking about here in terms of, you know, what is being measured and how does it relate to, like, is each shot of the measurement a single shot projective readout of the system, or is it some kind of expectation value, and yet you're still reconstructing a Wigner function? Can you explain that, please?
Okay, sure. So yeah, each measurement will be a single shot of a projection operator, which will be like the projection will be done, let's say, in a homodyne measurement by a local laser pulse, right? And that also amplifies the signal. So yeah, it's just homodyne measurements depending on the phase of the input laser pulse, and then from that data, trying to reconstruct the density matrix. Now plotting it is just a Wigner function. So Wigner function only appears at the end. So what the algorithm estimates is the density matrix based on the homodyne data.
May I add to this? So from an experimental perspective, you would measure, or you can measure in the output field using a homodyne technique, and then if you do this appropriately, you get something which is looking like a QCMQ function, and then you can do a state reconstruction, and if you manage to do that, then you can depict it in form of this Wigner representation. So you don't necessarily need a qubit, that's what I want to say, and I think that's the assumption here. But I agree with your statement that for the experimentalists, it's not intuitive that it's that there's no geometry going in there.
Okay. Yeah, I think the geometry not going, which is again like a viewpoint of only the magnet, nothing else around it. It is just a matter that for larger volume, you can input more power, right? Without burning the sample up.
Sorry, but in a Faraday measurement, you know, it's the interaction path length that determines the Faraday rotation, and that adds to the signal to noise ratio. So if I just, at any given power, so if I just pick one power and has nothing to do with, you know, a bigger sample, I can put more power in, but even if I keep power fixed and I just have a longer interaction length, I rotate more for a given projection of magnetization. So that's the part that I'm struggling with.
So
That's not that angle.
I understand that, but I don't understand exactly what that angle
So okay,
is.
so I guess the main point is, so the scaling of Faraday rotation is different than scaling of BLS. So you're talking about the intuition of why BLS is a different scaling than Faraday rotation? That understand? Yeah. Okay. Yeah, because Faraday rotation does not care about magnons. So I think it does not really, it's the static magnetization effect. Yeah, the rotation per unit length is of course proportional to only magnetization. I'm just trying to see how can I see it in equation, like where the volume is coming from. It's also, yeah, it does not depend on power, right? Faraday rotation is just rotation. It doesn't depend on power.
So you made a
That's
very
the big
important
difference,
point,
maybe.
which is that Faraday rotation doesn't care about magnons. But
Yeah.
is this so maybe the thing that I'm not understanding properly is the kind of interaction time. So, you know, for instance, if I think about a pulsed probe, I can measure magnons with a pulsed probe because I have a different Faraday rotation at a particular time because of the precession of the moment. And if I have superposition of two then actually, and I'm measuring an expectation value in the weak limit, then I actually will measure nothing, right? But if I have a single, not superposition, but just a deflection of the moment, then I would measure something. So maybe you can explain how it is, like, so I follow the operator, the math, but there's a kind of physical intuition that I think I'm just missing. And I'm not saying that you're doing a bad job presenting.
No,
I'm
no,
just slow.
Yeah, I mean, I'll not explain this project, to be fair. So it's like, yes, obviously the questions are reasonable. So the intuition of a light coming in and what is it coupling to? It says coupling to the fluctuations in this case, of course, unlike Faraday rotation. And if you think of magnetization as a time varying magnetization, then okay, you can think of as like the Faraday rotation, but at a slightly different angle at every frequency. And the output will, that means will be modulated at that Magnon frequency, right?
So this is a CW input, and then you're imprinting the magnetization frequency onto that.
Yes.
I got it. Thank you. That's extremely helpful.
Sorry, can you explain how it is that you have an imperfect reconstruction, or what the assumptions are, though? Because if you go to the next slide, so the noise term, normally it would average to 0, and it, you know, for a finite amount of signal, then you have a finite amount of noise. But if you average long enough in these experiments, typically M signal should reach a finite average at any given time, right?
But
a noise would reach a 0 average.
Yes.
And so if you were to average enough, why is it that you can't reconstruct the Wigner function?
It's because we care about the variances of the noise as well. With average, you can only get the average amplitude of the magnetization, which is not sufficient to reconstruct the whole density matrix. It will only give you the average component, average of M operator. But in principle, to get the whole density matrix, we need like average of
so
M
you're going
square,
to
M
reconstruct
diagram.
the density matrix assuming, are you assuming Gaussian? A Gaussian, it's obviously not Gaussian state,
noise,
so
yeah, I mean, it will turn out to be Gaussian. So I'm assuming white noise inside the material.
And then you, so you calculate higher order correlation functions, and those include the noise directly. Oh, okay, thank you.
Again, my apologies for stopping your talk, but it's interesting, so I'm keeping these questions. So the assumption about, the expression is representing the vacuum noise and fundamental uncertainties only. So these calculations and the reconstructed Wigner functions are not accounting for any technical noise, which in fact usually dominates everything. If we get to fundamental noise, then we are so wildly thrilled, and it almost never happens. But okay.
Although, I mean, Yig has reasonably high absorption, so okay, but yeah, it might be true. Yes, so it will appear in the theta. Yes, it will reduce the theta quite a lot. Now, but yeah, just as a point, this is, I don't know, a theoretically interesting point for me. It's like that even for a low theta, you can still estimate the correct peaks, but you just lose information about coherence. Which obviously, if I now artificially increase signal to noise ratio, you can reproduce coherence. So it's not a problem of the algorithm, but actually it turns out it's a problem of the data itself. That quantum coherence is just a lot more sensitive to noise compared to the classical information of the system. And therefore, any algorithm will have this problem in principle. Okay, maybe I want to go to the next part. Okay, the project that I wanted to discuss a bit more in detail. I don't have much time, right? So, okay, okay. 10 minutes. Okay, I'll try to maybe like go from the system to the results kind of situation. Yeah, so here in this project, the main motivation was that, my boss, Christina, she's kind of obsessed with skyrmions, especially quantum skyrmions. So she now she has lots of theoretical works on it, not just her actually, also from different groups around the world. There are lots of theoretical works kind of imagining or like proposing the quantum properties of fermions or developing theories for that. But at that point, as far as we know, there is no experimental evidence to show that fermions even show quantum behavior, because they can be relatively big. They can be like 10 to 20 lattice sites, and they might just, everything might just dephase out, right? So the idea of this project was to try to come up with a signature where you can see the difference between the classical dynamics of fermions and the quantum dynamics of fermions, and that's going to come by optics. I'm always stuck here. Okay, maybe it's interesting to discuss a bit about what the fermions are. So fermions are this kind of a defect where the ground state of the whole system is the ferromagnetic ground state, but if you flip a spin in the center, and then it will slowly, the flipping will, by exchange constant, will go around the rest of the material, and this forms a metastable state. It's really a minima with a very high energy barrier. In frustrated magnets especially, I'm not showing the Hamiltonian here, but it's very easy to see that it has a symmetry that you can rotate any spin. If you rotate the entire system by around z-axis by any angle, the Hamiltonian does not change. And because of that, this and these and all these three states, which are just rotations of each other, are all degenerate. They all form a large ground state manifold, which also means that we kind of have this degree of freedom, like a 0 degree of freedom called helicity, which I'm marking here. So I'm showing helicity pi by 2. Don't worry about the actual number, pi by 2 minus pi by 2, but this is the kind of variation which we're expecting when we talk about helicity. To study helicity, you have to look at its, oh wow, there's a font problem here. This should be S. Yeah, I just switched my PDF from Ubuntu to Mac, and this is the situation, I guess. So yeah, to study helicity, you have to look at its conjugate momentum, Sz, the spin, total spin of the magnet. It's a conjugate momentum, which you can easily see because we are talking about rotation, and the generator of rotation is Sz. So this is a conjugate momentum because of that. Oh, okay. These are again SZs, and yeah, that the Hamiltonian for a system which Christina derived already. Yes, sorry.
I have a question regarding your title in the slide before.
Okay.
So why do you need frustration there?
With another way to stabilize. Oh, it's for stabilization of fermion. This frustration helps in that. Typically, I mean, the general rule of thumb is that you need some kind of a length scale for this kind of textures to be stable, and frustration provides you with these length scale because it has like the nearest neighbor, the next nearest neighbors are kind of competing, and that leads to kind of gives you a particular length scale of how long will they become equal, in what length.
I'm asking because my question is if your next slides rely on the fact that your material is frustrated or not, because in principle you can have fermions also in non-frustrated systems.
Yes, so with DMI you mean, right?
Yeah.
Yeah, with DMI the only thing is the helicity will not be a degree of freedom because it's not rotationally symmetric around Z. DMI breaks that symmetry.
Okay.
Yeah. Okay. Yes.
I think I can complement this answer a little bit more. So for when you don't have frustrated magnets, you can have like fermions living at the same frequency range as magnons. So in that sense, they're going to be like less stable. But for frustrated, we showed that, well, not we show, but literature shows that the fermion states, the energy of the fermions are way below the magnon ones. So they're not going to interact like elastically with the magnons, and hence they're going to be like more stable. So that's essentially like the very importance of realizing magnetic fermions in these frustrated magnets.
Okay, maybe, okay, so we don't have to worry about Hamiltonian much, just to know that, okay, we can calculate the eigenmores of the system. I think so. I want to maybe go more towards the optical part of the system. So that's the main point of the talk. Keep in mind. Okay. So we first did a. Wow, this doesn't work. Yeah. Okay, so the first one of the talk. So as promised, I said that I'll compare the classical dynamics and the quantum dynamics of skyrmions and see if the optical signals are different or not. So just a simple system, if you look at the figure for the time being, that there's a skyrmion and there is just a classical coherent light coming in. And if you look at just the spectrum of the output, so there is nothing quantum in the measurements. It's simply the usual BLS measurement and usual spectral output. And we can forget about the formula for the time being. Let's look at what the conclusions are out of calculations, essentially. That the scatter light is just proportional to the input. So I'm writing the electric field here, but you can think of it as photon amplitude. That the scattered light at some frequency is proportional to the input light times the SZ operator, the total SZ operator. The reason it only cares about the total SZ operator is because these skyrmions are really small, while the light beam will typically be at least lambda by 2, while the skyrmions are like 10-20 nanometers or something like that. So it only cares about the average properties of the skyrmion, and that's why we have an average operator here. In this geometry, I'm not going to go into details, but if you know the selection rules for BLS, it's very clear that there is no signal from Magnon, so we only care about the skyrmion. And the main point is that because SZ is real, essentially, we have a frequency symmetric output, that the output at plus omega minus omega relative to the input frequency is same. That's really important, that if you know from BLS, it does not happen normally in other magnetic systems. In Magnons, this symmetry is typically broken in classical case as well. But here, the system is symmetric enough that we have this symmetry, which is quite nice because this symmetry is broken in quantum dynamics, which I want to show here. Okay. So the exact same system as I showed before. Nothing changes. The only thing is now we are analyzing the same system quantum mechanically. The quantum mechanical Hamiltonian, you can ignore. You only have to focus on these three terms, which is, this is the annihilation operator of a photon, the creation operator, and this is the SZ operator. And what we're talking about is just the scattering of light from K to K prime with some polarization sigma and sigma bar via the operator SZ. And now it's a relatively simple input-output theory calculations to show that the output scattered photons here at some frequency will just be given by the power spectral density of SZ operator. So you're directly sensitive to that power spectral density. Sorry for making so many equations, but I guess here's the main point of this slide, where if SZ at different times commute, then this scattered output will be symmetric in frequency. So it's kind of like if SZ is behaving classically, then we have a symmetric spectrum. Otherwise, we may not have. Okay. So now I will not maybe talk about many of the details in between, but let me show what the results look like. And wow, this plot is so much worse than I thought. Yeah, so what am I plotting here? If you just look at the plot, not the equation for the time being, that these are number of photons output, and this omega is relative to the input frequency. Kappa opt encodes the dissipation of skyrmion via radiation of photons. So if you, of course, if you input laser power, then skyrmion, because of BLS, can radiate out photons, which leads to losses. And so these are two different values of kappa out. Don't worry about the actual number, but just like this is a smaller value, this is a higher value. That's all that matters here. For a smaller value, there are these asymmetries. Now these asymmetries are nothing special. They are the consequence of basic quantum mechanics, where just because you have, like, if you're talking about this scattering, which is actually scattering between the second eigenmode of the skyrmion to the first eigenmode, while this one is from first to second, it will be higher because there's a higher population in first compared to second. That's the only reason behind these asymmetries. Of course, if you have a higher input power or somehow higher optical, for whatever reason you have higher magneto-optical coupling, effective one, then eventually optical photons will start heating up this fermion eigenstates, and the population becomes equal, and we start losing this asymmetry. Now, obviously, if you want to discuss more about the details of how it compares, I'm open to questions, but maybe it's good to end the talk now. So it's just I'll just hold you on the summary where, like, yeah, we modeled this different kinds of scattering with fermions and looked at the sideband asymmetry in the output photons, and that's supposed to be a smoking gun for. So yeah, if it's observed, it's supposed to be a smoking gun for the quantum behavior of fermions. So thank you for your attention.
Thank you. Do we have time for a quick question, or should we move on to the next?
So I had more time to think about my talk from before.
Okay.
So basically, the Wigner function can be reconstructed from the two-point function, just from the second-order correlation function of the output, right?
No, that only if it's Gaussian. Otherwise, no.
Well, so what you reconstruct is an effective representation of the state that would give you all the information about the state if it were Gaussian, no? Okay, maybe I'm misunderstanding.
Yeah,
I was just wondering why you can't calibrate out the noise, because if you calculate these correlation functions, you know, the noise is not correlated with the signal, and so you get two contributions. You get a contribution from just the noise, presumably the vacuum fluctuations. And you get a contribution from the signal that
but
you're
okay,
looking for.
at the least, if you're measuring, no, I mean any higher. You want to answer the question? Okay, Hansen.
Well, while the microphone moves.
Okay.
So I mean, I understood the reading out of the Magnon in the first one. Is it like your Magnon is an optical mode rather than a Magnon mode, and you fire it at a beam splitter, and then, but unfortunately, most of that Magnon, the light that you're assuming, you know, the Magnon analogous light is being transmitted and not going towards your detector, right? So it's like you're trying to reconstruct the quantum state of an optical mode after losing, in a linear passive way, most of it, right? And I would have thought, like, in principle, you can still reconstruct that state, even if that loss is quite high, but you might have to, like, switch to quadruple precision with your numerics, right? Because it becomes the you know, a cat state, there's not very much of that left after it's gone through some big loss. So, I mean, I think that's, so the picture you showed looked to me more like something that you would get if you were sort of seeing how well you could do experimentally rather than how well you could do theoretically in practice, right?
Sure. Yeah, I mean, yeah, the amount of, let's say, the difference between the probability distributions compared to coherence, like, I mean, a measure of how much information is lost is actually exponential in the separation of the superposition. So yeah, I mean, you're right. In principle, there must be a number of data points which will give you perfect simulation, but I guess exponentially increasing. Yeah.
And in the kind of quantum optics world, right, one place you can do things that are interesting, even if you've got a reasonable amount of loss, is if you're doing kind of single photon stuff, so photon counting rather than like homodyne measurements, right? Like the people who do continuous variable quantum optics experiments really care about every bit of loss, whereas the single photon people get away without worrying it most of the time, right? So I'm wondering if that's
I think the main problem here is not the measurement part, but just the output which is coming out of magnet, that those photons, they themselves have lost a lot of information about coherence.
Yeah.
So then I don't think the measurement will change that factor.
Yeah, I would like to add
Yes.
to this from a technical side. So the quantum optics experiments in the microwave domain, they typically suffer from this technical noise, which comes often in the form of the first amplifier stage, which adds you 20, 40 photons. And you can actually reconstruct it away if you have a known input state. And then quantum state reconstruction techniques like max likelihood estimates or so help you in order to be able to reconstruct this, even if you have a decent amount of amplifier noise, which I would kind of put in the category of technical noise. But you need to average and get very high quality histograms in order to do this, and have the reference states that you know of. And these are typically, you can refer to thermal states as reference states, or you have prepared some quantum state where you have a high fidelity quantum state, and then use this to calibrate your system and your noise, and then you can fold it out.
Yeah, I still believe like it's somehow, let's say even if you improve the algorithm, the problem is in the data itself. That just the data coming out of magnet has lost that information of coherence. So it will be a little bit, so calibration will help, yes, I understand. It will reduce the number of data points, so it will be required to judge that very tiny information from coherence, I agree. But I somehow feel like the main problem is still that it's the information exponentially going away for coherence. So, yeah.
Yeah, I wanted to address that exact point. So thank you for saying exponentially going away. So how does the theta parameter depend on the interaction time? So you have some Magnon state, some cat state, or whatever it is, and you're shining. You have an input state, and you shine it through the material, and you're imprinting. You're modulating that light.
Yes.
You're imprinting the Magnon state,
Yes.
right? And then that is a time varying thing. So the magnons are now decaying. So what are you assuming? What are the inputs for this? Does that question make sense?
Yeah, it makes sense. I think hopefully I also get the context you're referring to. So here I assume a pulsed input. So I want the pulse to be much shorter than the Magnon lifetime for that exact reason, that they don't want to deal with Magnon decays.
So the pulse is shorter than the Magnon lifetime, but longer than the 1 over the FMR frequency, or whatever the characteristic Magnon frequency. Is that correct? Because if you're going to imprint a modulation, the light has to be there for many, many cycles, I guess. You can't print if you used a femtosecond pulse, you just get a stroboscopic snapshot of at that instant of time. But then you can't demodulate it.
Okay, no, I understand. Yeah, I think I understand your point. I was just trying to see in equations. Yeah, that is something similar will occur because you'll not be able to resolve the output photons from input photons spectrally. That's probably an equivalent way to saying what you're saying, right?
Yeah. So
okay.
So
yes, that's
you have
true,
a pulse, and it's in between those two timescales. And is that accounted for in the analysis?
Yes, yeah.
So can you give us a rough time, like what you're assuming? I mean, maybe you did it in a way that doesn't lead to a real number. Maybe it's just a ratio or something, but can you give us a sense?
Yeah, I mean, I was thinking of time scales of like 10 nanoseconds or something like that, 10 to 15 nanoseconds. Yes, but I did not think deeply about it because it does not appear in theta. Because the same logic that if you have a smaller pulse, then you can input more power, but you have a smaller signal coming out. So that also cancels out. So I did not think deeply about it, I must admit. But yes, I was imagining something like 10 to 15 nanoseconds.
Well, the reason I'm asking is that when you demodulate, then the bandwidth of your pulse, you have some bandwidth, and then you imprint onto it, and those things become convolved. So your frequency resolution depends on the length of your pulse.
Yes.
And so that is going to go into the selectivity, it's going to go into the histogram that you're trying to generate.
Yes. So that I did, yes. For this protocol, I did not assume like they're very well separated. They're just, I assumed to be separated by like 2 line widths of magnons. So in principle, 2 line widths of magnons would be like 75 nanoseconds or 100 nanoseconds, something like that.
Okay.
Yeah, so this is accounted in the calculations. Yes.
Okay, thank you.
Okay, so maybe we can continue with the questions in the coffee break, and let's take Sanchar again. No, after the next talk. All right. Thank you, Sanchar.